Good night, sir, and everyone. Group 1 was tasked to discuss how groups 1 and 2 elements form the following compounds, that is, hydrides, halides, oxides, carbonides, and complexes, and also to discuss the trends of the periodic table. My group members include myself, Darshini, Divina, Purnima, Jasmine, Hemati, Rosalie, and Christine. Now, before we begin, let's touch a bit on what is electronic configuration. Now, it is defined as the distribution of elements into the orbitals of an atom, which is equal to the number of protons, that is called the atomic number. The diagram shows the electron configuration chart, and as demonstrated, potassium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. On the next slide, we will talk more about electronic configuration and the periodic table. So elements in the same group display similar chemical properties because they have similar electronic configurations. There are 7 periods in the periodic table. As you move along a period, the properties of the elements slowly change from metals on the left-hand side to non-metals on the right-hand side. The elements in the periodic table are arranged in such a manner that they are trends in their physical and chemical properties in a particular group and period. Looking at the electronic configuration of elements in the periodic table, we can immediately see similarities between the elements in the same period and in the same group. The table below summarizes the electronic configuration of the first 20 elements of the periodic table. The similarities in the electronic configuration of elements in the same group are all elements in the same group have the same number of electrons in the outermost shell. The number of valence electrons is equal to the group number, and all elements in group 0 have the full outermost shell. The similarities in the electronic configuration of elements in the same period are all elements in the same period have their outermost electrons in the same shell, and the period number is an indication of the number of occupied shells in an atom. That is the number of shells that contain electrons. Now we will look at the trends of the periodic table. They are considered to have 7 types of trends. These include 1. Valency, 2. Atomic radius, 3. Metallic character trend, 4. Non-metallic character trend, 5. Electronegativity trend, 6. Ionization energy trend, and 7. Electron affinity trend. So you may wonder what periodic trends are. Well, they are considered to be the change in the properties of elements down the group from top to bottom and across the periods from left to right in the periodic table. So one of the trends mentioned is the valency of an atom. As you already know, the valency of an atom is the number of electrons it has in its outermost shell. However, one can determine the valency of an atom simply from its position in the periodic table. The diagram shows that as we move across the period from left to right, the valency of the element first increases and then decreases. While moving down the group from top to bottom, the valency of elements remains the same. The next trend is considered to be the atomic radius trend. Now, this describes how the atomic radius changes as you move across the periodic table of elements. As shown in the diagram, atomic radius decreases from left to right within a period. This is caused by the increase in the number of protons and electrons across the period. One proton has a greater effect than one electron, thus electrons are pulled towards the nucleus, resulting in a smaller radius. Also, the atomic radius increases from top to bottom within a group, and this is caused by electron shielding. Next, we have metallic character trend. This describes the set of chemical properties that are associated with the elements classified as metals in the periodic table. Metallic character depends on the ability of an element to lose its outer valence electrons. As shown in the diagram, by going left to right across a period, it decreases. However, by going from top to bottom down the group, it increases. On the next slide, we have non-metallic character trend. This basically states that elements have a tendency to gain electrons. This basically states that elements that have a tendency to gain electrons are nonmetals. The tendency to gain electrons increases on moving across a period due to an increase in the nuclear charge and decrease in the atomic size. As shown in the diagram, as we move across the period from left to right, the nonmetallic character of elements increases, while moving down the group from top to bottom, the nonmetallic character decreases. I will now hand you over to my colleague, Hemoti.
Electronegativity trends. Electronegativity refers to an atom's ability to attract the electrons that are present in a chemical bond or when that atom is a part of a specific compound. It is a trend that moves across the periodic table from left to right. Hence, it increases, whereas going down the group from top to bottom, it decreases. This is basically shown in the picture here. Next slide. Electron affinity trends. Electron affinity reflects the ability of an atom to accept an electron. It is the energy change that occurs when an electron is added to a gaseous atom. Atoms with stronger effective nuclear charge have greater electron affinity. It is often reported in units of kilojoule per mole. The reaction that occurs when an atom takes an electron may be represented as a given formula. Next slide. As the given formula here. It can also be defined as the amount of energy needed to remove an electron from a singly charged negative ion, which can be represented by the second formula here. Electron affinity is one of the trends that can be predicted using the organization of elements in a periodic table. It increases when moving down an element group, as that is the column of the periodic table, and it increases also when moving from left to right across the element period. That is the periodic table row. The exception is the noble gases, which are in the last column of the table. Each of these elements has a filled valence electron shell and an electron affinity approaching 0. Next slide. The uses of electron affinity. It has a practical application and is used to measure chemical hardness, a measure of how charged or readily paralyzed Lewis acid and base are. It is also used to predict electronic chemical potential. The primary use of electron affinity value is to determine whether an atom or molecule will act as an electron acceptor or an electron donor, and whether a pair or reactant will participate in charge transfer reactions. Now, when it comes to the trend of an electron affinity, it is basically increasing when going from left to right across a period. Note that the overall trend across the period occurs because of an increased nuclear attraction. However, going down the group, the electron affinity should decrease since the electron is being added increasingly farther away from the atom, less tightly bound, and therefore closer in energy to a free electron. This is basically shown in the diagram that was on the first slide of electron affinity. Next slide. The final trend is ionization energy trend. Ionization energy is the energy that is required to remove an electron from a gaseous atom or ion. It is said that the initial ionization energy of an atom or molecule is the energy required to remove 1 mole of electrons from 1 mole of isolated gaseous atom or ions. The higher the ionization energy, the more difficult it is to remove an electron. Therefore, ionization energy is an indicator of reactivity. It is important because it helps to predict the strength of a chemical bond. Ionization energy is reported in units of kilojoule per mole, or electron volts. The first, second, and subsequent ionization energy. The first ionization energy is the energy that is required to remove the outermost valence electron from a neutral atom. The second ionization energy is that required to remove the next electron. It is always higher than the first ionization energy. Take, for example, an alkali metal atom. Removing the first electron is relatively easy because it is the last that gives the atom a stable electron shell. Removing the second electron involves a new electron shell that is closer and more tightly bonded to the atomic nucleus. The first ionization energy of hydrogen may be represented by the following equation that is given below. The general trend is for ionization energy to increase moving from left to right across the element period. Moving from left to right across the period, the atomic radius decreases, so electrons are more attracted to the closer nucleus. The general trend is for ionization energy to decrease from moving from top to bottom down a periodic table group. Moving down a group, a valence shell is added. The outermost electrons are farther from the positive charge nucleus, so that they are easier to remove. This is basically shown in this picture here. I'll now hand you over to my colleague, Purnima.
I'll be looking at the periodic table group 1 elements. What are group 1 elements? What are alkali metals on the periodic table? The alkali metals are considered to be lithium, sodium, potassium, rubidium, francium, cesium, as shown in the diagram. Each of the elements mentioned has its own use. For example, for mobile phones. For sodium, it is used as a heat exchanger in some nuclear reactors. For potassium, it is highly used in the making of fertilizer. For rubidium, it is used for vapor turbines. For francium, it is used for diagnostics, curing cancer. And for cesium, it is mostly used in the thermionic generators, which convert heat energy into electrical energy. Now we'll look at where are alkali metals located on the periodic table. Alkali metals are located in group 1 on the left side of the periodic table. As you can see from the image, which clearly shows you where alkali metals are located. Now we will look at the electronic configuration of the alkali metals. Electronic configuration for these metals are shown below. Lithium, sodium, potassium, rubidium, cesium, francium. And as you can see, these are the electronic configuration. Now we'll look at what are group 2 elements. What are alkaline earth metals? Group 2 elements are the alkaline earth metals. It consists of beryllium, magnesium, calcium, strontium, and barium, as shown in the diagram. Each of the elements that are mentioned has its own uses. For example, beryllium, it is used as a pacemaker, CAT scanner, MRI machines, etc. For magnesium, it is used to treat widely skin-related problems and attention. Calcium, it may be used as a reducing agent in the process of metal extraction. For strontium, it is used as medicine, and for barium, it is often used as a spark plug, electrodes, and in vacuum tubes as a drying and oxygen removing agent. Where are alkaline earth metals found on the periodic table? Alkaline earth metals are found in the second group of the periodic table. The image shows you where alkaline earth metals are found on the periodic table. Now we will briefly look at the electronic configuration of the alkaline earth metals. The electronic configuration of alkaline earth metals is given in the table below. The elements are beryllium, magnesium, calcium, strontium, barium, and radium. And these are the electronic configurations.
On the next slide, we will look at the basic physical and chemical properties of group 1 elements. Now, the table shows some properties of these elements. It demonstrates the proton number, nucleon number, density, hardness. On the next slide, we will look at basic physical and chemical properties of group 1 metal. Now, on the table shows some properties of these elements. It demonstrates the proton number, nucleon number, density, hardness, both melting and boiling point, the atomic radius, and electronegativity, at which each has its own values. However, if you look at the element francium under the hardness column, it is considered to be unknown. On the next slide, we will talk about the physical properties of group 1 elements. It is known that group 1 elements or alkali metals are gray solids with shiny silvery surfaces when freshly cut. These surfaces turn dull when exposed to air. This is because alkali metals are very reactive. They react rapidly with oxygen and water vapor in the air when exposed. Alkali metals are considered to be soft solids and can be easily cut. They have low densities as compared to heavy metals such as iron and copper. They are also considered to be good conductors of heat and electricity, and they have a low melting and boiling point as compared to heavy metals such as copper and iron. On the next slide, we will talk about the chemical properties of group 1 elements. It is said that the atoms of group 1 elements all have one electron in their outer shell. This means that the alkali metals all have similar chemical properties. That is, number 1, reaction with moist air. Group 1 elements basically react with moist air. It is stored in oil to stop air and water vapor from coming into contact with them. Moist air reacts with potassium to form potassium oxide. This creates a layer over the surface of the metal. Number 2, reaction with water. The alkali metals react with water to produce a metal hydroxide and hydrogen. For example, sodium reacts with water. That is, sodium plus water forms to give you sodium hydroxide plus hydrogen. And this is also shown in the balanced equation given below. Sodium hydroxide is an alkali. It is a base that dissolves in water to form an alkali solution. This solution has a pH greater than 7, and it turns universal indicator solution blue or purple. Now, on the next slide, we will look at the physical properties of group 2 elements. Now, some physical properties of these elements are they have low density, that is mass over volume. They have low melting points except beryllium. They also have low boiling points except beryllium. They are soft and strong in their metal state. They are considered to be ductile and malleable. They're also shiny and silvery as metals, as well as having a dull appearance, and these metals can be found in the earth. On the next slide, we will look at the chemical properties of group 2 elements, and these include that they are relatively reactive. They form halides when reactive with halogens. They also form oxides when reacting with air, leading to a dull appearance in its pure form. These metals form 2+ charge in cationic form. They also have anionic bonds with other negatively charged anionic forms of elements. Examples of common compounds are calcium carbonate and dysprothium nitrate. On the next slide, we will look at how does group 1 and 2 elements form hydrides, carbonites, halides, oxides, and complexes. I'll now hand you over to my colleague, Purnima.
What are hydrides? A combination of any element with hydrogen is called a hydride. Hydrogen is such a common component of many materials, usually in a hydride. The hydrogen has the oxidation number of -1. Some of the most popular examples include water, methane, and ammonia. So when hydrogen reacts with any other element, the product form is considered to be a hydride. There are 3 types of hydrides. These are ionic or saline hydrides, a hydrogen bond with electropositive metal that is alkaline metal or alkaline earth metals. The second type is covalent hydrides, are hydrogen and nonmetals where bonds electron pairs are shared by atoms of comparable electronegative. And the last type is metallic hydrides, which are discrete molecules or metal clusters in which there are atomic centers in a defined multi-centered and multi-electron bonds. Note that group 1 elements are alkali metals and group 2 are alkaline earth metals. Now, how does group 1 and 2 elements form hydride? Hydrides of the group 1 elements are ionic and contain the H ion. The group 1 elements react with hydrogen to form ionic saline hydrides with the rock salt structures, the ammonia present in the hydride ion H. The hydrides react violently with water, that is NaH solid plus H2O liquid, which gives us NaOH aqueous plus H2 gas. This is where heavy element hydrides such as the tin hydrides frequently undergo radial reactions, in part because of the low EH bond energy. You may wonder what I mean by the EH bond energy. This is the oxidation reduction potential. However, the boron hydrides are called electron deficient compounds because they are easily reduced by hydrogen. That is NaH solid plus NH3 liquid, which gives us NH2, ammonia plus H2 gas. Now, what are carbonates? Carbonate is an ion consisting of 1 carbon and 3 oxygen atoms, or a compound that contains these species is its ion. The molecular formula for the carbonate ion is CO3 2-. How does group 1 and 2 elements form carbonates? The group 1 carbonates are soluble and decompose of their oxide when heated strongly. The elements form the only soluble carbonates, with the exception of the NH4 ion, although lithium carbonate is only sparingly soluble. Sodium carbonate with overall reaction, which uses the commonly available feedstocks of NaCl and CaCO3, can be represented by the equilibrium. Ammonia and carbon dioxide, that is from the thermal decomposition of CaCO3 and NaHCO3, are passed into a saturated sodium chloride solution to form a solution of NH4, NaCl, and HCO3 ions, which give us the equation of NaCl aqueous CO2 gas, NH3 gas, H2O liquid will equal to Na aqueous, HCO3 aqueous, NH4 aqueous, and Cl aqueous, where it is heated with silica to form sodium silicate, Na2O SiO2, and it is then removed the Ca2 ions as a calcium carbonate. Now, how does group 2 elements form carbonates? The reaction between beryllium, magnesium, calcium, ruthenium, and barium with CO3 are all insoluble in water and unstable to heat. For example, beryllium carbonate, magnesium carbonate, calcium carbonate, ruthenium carbonate, and barium carbonate. Thank you. I'll now hand you over to my other colleague.
What are halides? Halides are compounds of halogens and exist in nature, especially in water, due to their high solubility, and they arise from natural bedrock of running water and industrial runoffs. They consist of a halogen anion, also called a halide ion, and a cation, and they are present in nature, such as salts and acids, which are essential to human life, and they can be found in minerals, animals, and plants. Some examples of halides are sodium chloride, which is the most known one, hydrogen iodide, and methyl chloride. And now we'll look at the properties of halogens. So the halogen group, which is group 17, includes elements such as fluorine, chlorine, bromine, iodine, and astonine, and they all exist as diatomic molecules. So diatomic molecules meaning that they have only two atoms of the same different chemical elements. And at room temperature, fluorine is usable as a yellow gas, bromine is a red liquid, iodine is a purple solid, and astonine is a radioactive element and exists in nature in small amounts. And they also have high ionization energies and form the most electronegative group of elements. Next slide. Now we'll look at how does group 1 and 2 elements form them. So the elements' electronic configuration would allow them to easily react with group 1 and 2 metals because each halogen has a tendency to pick up one electron and group 1 and 2 has a tendency to lose 1 or 2 electrons. Therefore, the halogens would be expected to react more vigorously with group 1 and 2 metals of all elements from the main groups. So let's look at group 1 alkali metals. Halogen would react vigorously with all alkali metals and produce salts such as NaCl and KCl. And these are the most industrially important ones because NaCl is used to preserve meats and to melt ice on roadways. And KCl is very important for plant fertilizers because of the positive impact of potassium on plant growth. Now, group 2 alkaline earth metals would tend to lose the electrons, and halogen atoms tend to gain electrons, so they would react to form hydrated halides and are ionic, except for those involving beryllium, which is the least metallic of the group. And here we have a reaction example. We have Na plus Cl will give you 2NaCl, or known as sodium chloride. Now let's look at what are oxides. An oxide is formed when oxygen is combined with another element except the lighter inert gases such as helium, neon, argon, and krypton. An oxygen forms at least one binary oxide with each of the elements. This means that they are compounds of oxygen with another element. Some examples of oxides is silicon dioxide, iron oxide, carbon dioxide, and aluminum oxide. And here we have some pictures of what they would look like: the silicon dioxide, iron oxide, carbon dioxide, and the aluminum oxide. Now, how does group 1 and 2 form these oxides? So group 1 elements reactivity increases as you go down the group. Therefore, their reaction with oxygen would get more vigorous as you go down the group. And the alkali metals burn vigorously when heated and is placed in a gas jar of oxygen, forming a white smoke of oxide. So the oxygen from the air reacts with group 1 elements to form metal oxides. The oxygen would react with the surface of the metal at the room temperature, and it then forms a white oxide covering the surface, but the metal below the surface does not react. Here we have another example with sodium plus oxygen giving you sodium oxide. And how do group 2 elements, group 2 elements and oxides. So group 2 elements, also known as the alkaline or metals, will react with oxygen and they require heating or burning, but they do not react as fast as group 1 metals. They are similar to group 1 in that their oxides and hydroxides are slightly soluble in water and forms alkaline or basic solutions. And all alkaline earth metals form oxides in air and at room temperature except for beryllium, and this is because it's unreactive with water and air. And the chemical behavior of beryllium is allocated to the small size and high ionization energy of its atoms. I'll now hand you over to my next colleague.
What are complexes? Complexes are considered to be the central metal ion that is surrounded by atoms. It donates lone pairs of electrons to form bonds to the central metal ion. Complex ions are considered to be a form of metal ion that is surrounded by ligands that are coordinately bound to the metal ion, forming a complex. It forms when compounds with unbonded electrons donate their electrons to the central metal ion. These compounds or elements that donate the lone pairs are commonly called ligands. That is what is demonstrated on the picture here. Now on the next slide, we will talk about how group 1 and 2 elements form complexes. Complex formation is considered to be the most significant for the smallest citation. This is because the electrostatic interaction of the metal cation with polar water molecules. Hence, electrostatic interaction allow alkaline metal ion to form complexes with certain cyclic polyethers and related compounds. Examples may include crown ethers and kryptons. Some examples are shown below. Therefore, in group 1 and 2, where there are inner d orbitals, they are so well shielded that an electron placed there is not tightly bonded, and thus it tends not to stay put. Somewhat ironically, the orbital become available to accept electrons from ligands just at the point wherein neutral atoms are being filled. This is because we added protons to the nucleus as we added electrons to the subshell. In truth, without readily available d orbitals with low charge density, except maybe lithium, and the alkyl metals are poor at forming complex ions. That includes complexing the hydroxide ions, thus explaining the unique basic strength of the hydroxide of these metals. On the next slide basically demonstrates what complexes look like. I'll now hand you over to my colleague Darshini.
Okay, conclusion. We basically learned what is electron configuration, and this is considered to be the spreading of electrons of an atom. We then talked about the different trends of the periodic table, which included valency, atomic radius, metallic character trend, non-metallic character trend, electronegativity trend, ionization energy trend, and electron affinity trend. Then we basically talked about group 1 and 2 metals, in which group 1 metals include lithium, sodium, potassium, rubidium, francium, and cesium, while group 2 metals included beryllium, magnesium, calcium, strontium, barium, and radium. We then learned the physical properties of these elements. For group 1, it includes that they are gray solids and they are said to be very reactive, whereas group 2 elements have low density and are considered to be shiny and silvery metals. Lastly, we learned about how group 1 and 2 elements form the following compounds, which include hydrides, carbonates, halides, oxides, and complexes. This is the end of our presentation, and these are our references. Thank you. And these are our references. Thank you.